So we've got a column coming down, or it could be a wall, and it sits on top of our footing. And the idea here is that we're just increasing area as we work our way down the building to distribute the load over something that has a lesser compressive strength. So you think about it in terms of, say, a steel column coming down, and it sits on top of a base plate. Right, the calculation that we already looked at for the base plate was coming up with the physical area of the base plate so that we don't exceed the compressive strength of the concrete that the base plate sits on top of. Well, this is basically the same idea, but now we're sitting on top of soil instead of steel on concrete. So we have our compressive load coming down here, and we're distributing that load out over a large enough area so that we're not exceeding the compressive strength of the soil. Now, I've drawn here a square footing, but of course footings can be of a variety of different shapes. Two most common are square and then a strip footing, where you've got a wall with a strip that runs all the way underneath the wall. You can have them as rectangular shapes, and you can even have weird ones where the corners are notched off and so on. These are done when you've got things like underground pipes that you're trying to avoid. Right? So you might make some changes to the geometry. You still want to maintain that area though. Right, so our design process starts out fairly straightforward. We're going to first of all determine what our area is. So we'll go through this in a step-by-step kind of process. So our area has to be greater than or equal to our P over our allowable soil-bearing pressure. Now this is PS, not PF. This is factor. This is not factored. So this is just dead plus log. And we come up with an area necessary. And from there, we will calculate a factored soil-bearing pressure by taking our PF and dividing by area. Right, we need our QF when we do our strength design calculations. So we're going to be calculating shears and moments essentially. And you'll notice by the configuration that we have in here that what we have in our footing, there's basically reinforcing at the bottom of the footing going in both directions. So from the perspective of a square column, it really doesn't matter which is on the top or the bottom, right? Whether these ones are on the bottom and this one's above it, or whether they're flipped around, right? Because what these are there for is our bending, right? So as I take a look at our footing here, right, it's going to bend in this direction. So we have bars going in this direction in order to be able to resist the bending, but it's also going to bend in that direction at the same time. Right, so this is where we get that two-way bending. And you'll notice in our configuration that we don't have any stirrups within there as well, and there's no bars along the top here, right? So as it's bending in this direction, right, our tension zone is at the bottom. Now there's a few minor little things. It's designed much like a slab in the sense that we want to position our, or size our footing so that we don't require any stirrups. Stirrups are rare in footings. So we've got, if you remember with our slab design, what we had was a shear calculation for figuring out our depth. Right? We started with an estimate of our depth based on what was necessary to avoid deflection calculations. And then we went and checked to see whether or not it could handle the shear. And if necessary at that stage, we make the slab thicker so that we don't have to put in shear reinforcement. So we do much the same sort of thing here. But for shear, now this is a two-way scenario. So we're going to go through and calculate two different shear calculations. Right, so one of them, we're looking at a shear plane that's, well, actually I'll draw that a little offset here. One is a shear plane like this. Right, this is our one-way shear action. And this occurs at a distance of dB away from the edge of the column. So again, it's just, we're looking at what happens right at this location. We're going to calculate our shear and determine the thickness of our slab or footing, basically, so that we don't require shear reinforcement. Now, the other one that we're looking at is with that punching shear that I talked about. Right, so punching shear is where this whole thing just pops right through. So it's a different failure mode or different failure plane. And what it is a failure plane that comes out like this. And it is located at a distance of d over 2 away from the column face. So notice the difference here, that two-way shear is based on d, whereas one-way shear is based off of dv. So we've got a separate shear calculation. So we're going to go through and check our two-way shear and check to make sure that our column doesn't require any shear reinforcing. And if necessary, at either of these calculations, we'll increase the thickness of the frame. So we have an initial calculation which gives us our area, right? And we work off of there to come up with our factored soil bearing pressure. This is what's actually pushing up from the bottom. We'll be using this as part of our shear calculation. And of course, our area is length times width. Right? And again, it could be rectangular. If we were doing a strip footing, so I've got a concrete wall and I want to put a footing under the wall, it is designed using much the same sort of methodology, but like we did with our slab, we look at a 1 meter wide design strip. Right? So I take a 1 meter wide design strip, so if we had our wall coming along like this, and then here's our footing in here, we're just going to take a 1 meter wide strip here. And that gives us one dimension of our area. Right? So our area now is 1 meter times whatever this dimension is, and that's what we end up solving for. The one thing that's nice about here is that in terms of our failure plane, with a strip footing, I only have to worry about one-way bending. Right? This is only bending in one direction only with a wall. So it's very similar to what we're talking about here with a square footing or pad footing. It's just with one shear check instead of two shear checks. Okay, so next we're going to check our shear requirements. So of course we want to set our VF equal to VC. In fact, I'm going to say VF is either than or equal to VC. Now for two-way shear,
VF's greater than VC, is that right?
oh, sorry. Yeah, no,
VC is greater than VF.
Yeah, that's it. Yes, yeah, no, it's written correctly. Yeah, I just said it. That's right. So yeah, so we want the shear of the concrete to be greater than what our factored shear force is. Now, in our two-way shear, we have this formula right here. So we have a little VC, which we'll be going and calculating. There are actually three formulas in the code, and we're going to look at just one of those formulas. It is often assumed that that is the governing factor, so we're not going to go check the other two, but in a full design, we would check all three of those parameters. Right, so we've got a formula that we'll use for little VC, and then we have our D value. Remember that two-way shear is based on D, and B0 is the perimeter of this line, right? So it's based on the size of the column. And then we've got our one-way shear calculation.
Is the perimeter of the function?
Yeah, that's right.
Sorry, can you go over those acronyms
So B0 is the perimeter of this line here. So length here
Of the
punching shear. Right, so at a distance of D over 2 from the column. Right, so if your column is 300 by 300, and my the footing is 400, right, I'm going to take D over 2, right, so 400 over 2, so 200 on either side, right, and then we're going to calculate the perimeter based off of that. Right, so we're finding, and so what we've got is a shear times a length, right, or times an area rather. And then our one way is, this is the same formula we looked at before, so this is capital VC. Phi C, lambda, beta, square root F prime C, EXW, and EB. Right? That's the same formula we looked at before for a one-way shear. Right? And if necessary in either of those calculations, what we'll end up doing is increasing the thickness of the footing. Now, what you'll notice here, again, yes?
What's D?
What's D?
Yeah.
That's the depth down to the centroid of the reinforcing steel. You'll notice when we do our D here, our calculation in an example, we've got two different rows in here, right? So we've got, it's not We're normally considering D to be the centroid of the row that we're actually analyzing. So when I've got two rows in here, I'm going to actually analyze based on the higher row, because that is the smaller value for D, so hence a conservative calculation. Some people actually take the average right in the middle here. There are some approximations that we look at in this calculation as well. Right, now again, our two-way shear is based on D, and our one-way shear is based off of DV. So typically what we do here is we start with our two-way shear, and we will calculate a required D, and then from there we will add in a bar size and a cover distance and so on, and that gives us our overall thickness. And then once I've got my thickness, I can actually calculate a DV. And we've got two separate formulas for DV, and then I can go and check my one-way shear. So we use our two-way shear in order to come up with a D and come up with a thickness, and then I check the one-way shear from that to see if it works, and if not, then I increase accordingly. After we've checked our shear, we're going to go and look at our moment. So moment resistance has to be greater than our factored moment, and we'll go through our normal calculations in here. We do have a minimum requirement. Just like with our slabs, we have an AS min is 0.002 gross area in both directions. And this applies as well for strip footings as well. Strip footing, even though bending occurs only in one direction, we put reinforcing in that one direction, we still actually have reinforcing going that direction as well. Right, and that's based on that minimum. Next we do a spacing check. Same as what we were looking at for slabs, we have an S max value. We want to check that our row is less than row balanced. And of course, as long as we're using the tables to come up with our required area of steel, then we're making sure that our row is less than row balanced. But just like we had with our beams, if we have something that is very heavily reinforced, you can end up with a scenario that you say you need 6.2 bars and round up to 7, and that round up is enough to push that over the limit. So that's just something to watch out for if the reinforcing ratio ends up being relatively high. And then the last thing we're going to do here is check our development length. Now for checking our development length, basically what we're doing is recognizing that our moment diagram, when we kind of look at this configuration here, our moment diagram is, let's sketch that underneath here. Right, we've got an axial load coming down here, and I have a UDL that is resistant based off of this. Right, so this is that QF that we calculate from here. Right, so I have a PF coming down here, and I have a QF coming down here. So our moment, so our shear diagram has something that looks like that, and then our moment diagram will look something like that. Now, technically, the way I've drawn this here is with a point load applied right in the middle. Physically, there is some size associated with it, so more appropriate is something like that. Right, where it goes up the column face and then varies across the width of the column itself. But again, what we're interested in is not calculating this maximum value, at least for our one-way shear. We're calculating that at a distance of dV. Right, so here's our column face. So we want to find our VF out here. Similarly, our moment. Moment is calculated at our column face, but it's not the absolute peak that's on there. So it's just a matter of finding the area under this triangle to come up with that moment. Right, so this is what we're looking at as our maximum moment. Right, and from our maximum moment, we develop our area of steel, and we go through the same kind of design principles we were looking at before. Calculate a KR, look up a reinforcing ratio. For the reinforcing ratio, I'll come up with how many bars and what size, and then I can go do my spacing checks and so on to go along through there. So when I do my development length here, what I want to do is make sure that the length that I have available from this point out to here, the end of the bar, is long enough to be able to fully develop that tensile strength that we're looking for. And this area here, if we're checking our development length, and it fails the development length check, so in other words, I need more length than I have available, we have two options. Either I can reduce the bar size, right? Say I try putting 30 M bars in there. If we go to a smaller bar size, I need a smaller development length. But the downside is then I'm putting in more bars and I might run into issues with spacing. But going to a smaller bar size will give you more available length, or at least you don't need as much development length in order to develop the bar. The other option, of course, is to increase the size of the footing. Right, so I just increase the size of the footing so that this length here is long enough to fully develop the tensile strength that I need for the bar. So that's basically the design process.
From the column?
Straight down to the column, yeah, that's right. There.
Right, so that the distance off is
And so I was drawing that from the one-way perspective, so that was the at DB. Right, and then again from a little bit different when we're looking at a punching shear, because there we're looking at the entire force, right? So our full PF is applied here, and punching through this area created by that perimeter and the depth. Right, so that's that's this area right here. So there's an allowable stress that's in the concrete, a shear stress, and then that's that area term, right? And that's that full punch through. Yes?
if that column is subject to moment, where is that moment applied, and would you also factor that into this equation?
Yeah, so if there is moment in there, what's happening is that the column then is going to actually go through some bending, right? And there could be some additional bending that takes place in there as well. So yeah, we would consider this roughly to be a fixed condition, right? So looking at that condition on the K table there. So it's not a 0.5, it kind of maxes out at 0.65, but there is moment transfer between the column and the footing, right? That's causing the footing here to bend as well, right? So if you've got a significant amount of moment there, then that's something you might want to add in as well. And of course, if you've got a rectangular footing, what you end up doing is designing in two different directions separately. Right? So you'll have a north-south direction and an east-west direction with two different moments potentially, and design configurations in the two directions separately.
Could you simplify it because it's a fixed condition and analyze it like a simply supported beam, essentially? Or a beam with a supporting UDL?
Oh yeah, so instead of like a UDL with a point load in the middle and have that fixed support there?
Yeah, or it could have a moment acting in there.
You know, I suppose you could. I've never actually seen it done that way though.
Okay.
But, yeah, there are some sophisticated programs out there that take into account a variety of different soil conditions. There's like a 6x6 matrix of soil deformations, soil shears. It can get quite complex. And when you get into those kind of really weird soil conditions, that's when you start looking at pattern piles and stabilizing the soil and all that kind of stuff. So this is just a quick and simple analysis. Now, one of the things that can sometimes happen for a building is if you've got a building that, say, looks kind of like the example we were doing in class, right, in the lab, right, we've got our columns that go around here, right, and, let's just simplify this a little bit here. Right, we've got columns that are going around here. And underneath those, we're going to put our footings. Right, so for the most part, we've got a footing that sticks out like this, and it's not too bad. Right, so you get the idea there. Now, we've talked about in the design of this footing, right, how we start with calculating our area, right, again, based on the allowable soil bearing pressure, checking our shear, doing our moment calculation, and so on. What we haven't talked about is the depth of this footing. And the depth of the footing can actually be critical. When we're talking about a tall building, the overturning moment on the building, right, as I apply an earthquake or wind force, is trying to push the building over. And what's resisting it is this footing being pulled up, and it's mobilizing a whole bunch of soil sitting on top of that. So if we think that there's a possibility that the building's going to get knocked over, what we want to do is put the footing deeper so that I can mobilize more soil. Right? And typically we're looking at a 45-degree angle, but it depends on the soil properties. So there's the depth side associated with it as well. Now, the deeper I put this, the more pressure that the soil is exerting as a load on here. Right, so just like having an object submerged underwater, right, there's water pushing down from the top, but there's also water pushing up from the bottom. Right, well here we've got soil pushing down from below and soil pushing up from the bottom. So if I just take the total force coming down here and use this to come up with this resistance, this doesn't necessarily take into account that this resistance also includes this force here. Now this force doesn't cause any bending, right? It kind of just passes through the footing. But what it does do is it increases the stress on the soil. So when we start at this point here with this Q allowable, technically what we should be looking at is net soil pressure. So subtracting off of that any soil pressure from the footing that you have placed above it. So the deeper that is, the more of an issue that's going to be. Right? So then that ends up making a bigger and bigger footing, which is not necessarily a bad thing, because if you're having to put it deep in order to mobilize that soil pressure in an uplift scenario, putting a bigger footing means you're mobilizing more soil, so that actually works to your advantage. Now, as we start putting our footings around here, if I try to put my footing in here, what we're going to find is that they actually overlap. And that's not uncommon to have a scenario where you have two columns that are relatively close together, so you end up with an overlapping scenario. So what we're now doing is analyzing with one big rectangle. So we would put our footing in like this. So we've got load coming out here and like that. So we're now analyzing it with 2-point loads instead of 1-point load. Right? So it alters the shape of your shear and moment diagram, but the process is we're still going to have on the left-hand side here, we still have this triangular shape. Find the area of that triangle and come up with our moment. Right? That process doesn't change. Right? So we don't really worry about the fact that we're overlapping. But what it does mean is that if I've calculated a size, right, and I take a look at this one here, that size is based on the compressive load that's coming down the column, right? And then the one next to it also has a size. So if I overlap them, what that means is I've actually reduced the available area. So we actually end up having to increase the area. Right? And it goes back to this calculation here, is we take the total load, right, from both columns and divide by allowable soil pressure to come up with our area. So we end up with a rectangular geometry, which is of a larger size than it would have been if you just kind of put the two together. Right? So that happens, and it's not uncommon that we run into that kind of scenario. Okay, let's go through a numerical example here.
In this class, will we run into that scenario?
Nope.